picking up where we left off, we're going to impute the derivative when f of x is equal to this polynomial function, x squared minus 8x, which is continuous. However, we don't have a defined value point. So this is where we're going to want to rely on the limit, or the derivative definition as h approaches 0 of f of x plus h minus f of x all over h. So what we need to first do is substitute this expression into each input. So we wind up with x plus h squared minus 8 times x plus h minus, now we're going to have a typical mistake, right? We're subtracting the entire function. So when there's more than one term, I suggest putting in parentheses. That way you don't make any careless sign mistakes. Right? And something typical should happen when you are doing the definition of the derivative. I'm going to do all the algebraic manipulation and skip the explanation there. If you need assistance, I'm sure at some point in time I'll put up a video of earlier mathematical concepts, but not right now. Okay, notice x squared minus x squared, negative 8x plus 8x, right? And all of my remaining terms have an h in them because I cannot currently substitute this in since I have an h in the denominator. But if I factor, right, these three terms, the h's, if you do the definition of the derivative correctly, and I hate using this word, will always simplify. Oops, that should be an h there, not a 1. Ooh. Thus, limit as h approaches 0 boils down to this much more simpler polynomial. We substitute it now since it's continuous, and the derivative of this function is 2x minus 8. As we acquire a little bit more experience, and you learn how to use these, do these using the power rule, the chain rule, quotient rule, product rule, so on and so forth. You can verify that you've done your definition correctly by applying the more efficient method. But this is critical to be able to understand what it is that you're exactly doing. Yeah, well, you can do derivatives, but do you know why you're able to do them and what is actually happening visually speaking? Because that's a big theme in calculus, right? We're really trying to understand a complete solid grasp of behaviors of functions graphically. Now, before we wrap up, we're just going to talk through the derivatives of linear and constant functions. So if f of x is equal to mx plus b, your stereotypical slope-intercept linear function, then f prime of a is equal to m, so whatever the value of the slope is for all a, and if f of x is equal to b is a constant function, and f prime of a is equal to 0 for all a. And the reason why this kind of makes sense, and we probably could have taught you this when you were in Algebra 1, is the first thing that we said that a derivative was the rate of change. Now in Algebra 1, you're conditioned to say m is slope, and you never really remember that slope is really the rate of change. So it makes sense that if a derivative is the rate of change, well, what's the rate of change of a linear function? Well, it's the slope, so the derivative would be the slope of a linear function. And vice versa with a constant function. A constant function looks like this. Rate of change must have some type of y, some vertical change, which, as we can see, there is none here. Therefore, since there's no vertical difference or vertical change, the rate of change would need to be 0. And that'll do it.